In this video, I'm going to talk about abstract algebra, group laws of exponent. So we'll start with a definition which will be essential for using in our proofs for the theorem later. So let G be a group and let A be an element of G. So this definition is about exponent, where if A has an exponent of 0, then it's equal to the identity element. Now, what is the identity element? It depends on the binary operation. It depends on the operation. If it's addition, then the identity element will be 0 because it is the number that will result to itself. If it's multiplication, then the identity element is 1 because any number multiplied by 1 is equal to itself. And then for n is greater than or equal to 1, meaning an exponent that is 1 and above, then it will be a to the n is equal to a to the power of n minus 1 times a. Alright, so this is applicable for greater than or equal to 1. Now, if it's negative integers n, meaning negative exponent, then it's defined as a to the power of n is equal to a to the negative n all to the power of negative 1. So it's kind of different definitions if it's 0, if it's greater than or equal to 1, and if it's a negative integer. Now, if you say a to the power of 3, based on the definition, as it's greater than or equal to 1, so it's going to be a to the power of 3 minus 1, which is the same as a squared a, which is the same as a times a times a, or if the operation is times. But this is a binary operation. We don't know what is the operation unless it's given, and so we're going to use a star symbol. So a star a star a. So it is repeating itself with the operation star as a in general operation. Now let's say, for example, the set G is a set of real numbers with under the operation addition. Okay, so this is a group. It satisfies all the requirements for it to be a group. And then let's get an element of a real number, which is actually 4. So 4 cubed is actually 4 plus 4 plus 4. So you might think that 4 cubed is 4 times 4 times 4 times 4, but it's actually not in abstract algebra or in group, because it depends on the operation that is going to be used with the star. So here the star is plus, and so our operation that will be followed will be plus. So if it's 4 to the power of 3, then it's 4 plus 4 plus 4. So it's the same as 4 times 3. So this is 12. So if it's 4 to the power of 0, and then it's not 1 like the usual we know, like any number to the power of 0 is equal to 1, because that is true for multiplication. But here again, it's addition. So any number to the power of 0 is equal to its identity. So the identity element for addition is 0, because any number plus 0 is equals itself. Now, if it's a negative exponent, so as we have in the definition, if we are going to substitute based on its definition, it's going to be like this: 4 to the power of negative of n, which the n is negative 3, to the power of negative 1. So if we're going to solve this, we will expect that the answer must be just the inverse of 4 cubed, because it's 4 to the power of negative 3. So the inverse of 12, of course, you will not think that it's 1 over 12, because we're not talking about times. It's add. So the inverse of adding is its opposite sign. So if the inverse of 2 is negative 2. The inverse of negative 3 is positive 3. So it's like that, because we have to put in mind that it's under addition operation. So of course the inverse of 12 is negative 12. So we are expecting that the answer must be a negative 12. So let us do this. So we will get the inverse of 4 to the power of negative and negative 3, because it's to the power of negative 1. So the inverse of that is a negative of the whole thing, because it's under the addition operation. Then we can make this negative negative 3 into positive. It's the same. And then we can expand the 4 cube into 4 plus 4 plus 4. So it will become 12. And that means 4 to the negative 3 is equal to negative 12, which is the inverse of positive 12. And that makes sense because it's 4 cubed and the other one is 4 to the power of negative 3. Now how about if we have this set G, which is R asterisk with under the operation multiplication. So you might wonder what's that asterisk mean. It means except 0. So it's a set of real numbers except 0. So I do that because it will not be a group if we include 0, because including 0, 0 doesn't have an inverse. So it will violate the requirement for a set to be a group. So removing 0, that becomes a group. And then we will take a real number, for example, 4. We're going to use the same value as the previous so that it's easier for us to compare. So 4 cubed here means 4 times 4 times 4, because the operation now is multiplication. And so it is 4 times 4 is 16, 16 times 4 is 64. So 4 cubed under multiplication operation is different from the previous example, which is addition. And then 4 to the power of 0 is equal to identity element, which is based on the multiplication operation. The identity element must be 1, because any number multiplied by 1 is just itself. Now if we are going to consider the negative exponent like the previous one, so it's again it's so that it's easier for us to compare the two. So we're going to follow the definition of a negative exponent. So it will be negative of negative 3 to the power of negative 1. So the inverse of 4 to the power of negative 3 will be, so of course, because this is multiplication operation, so the inverse will be the reciprocal, because any number multiplied by its reciprocal will result to an identity element. So that is its inverse. Now we're going to simplify this. Negative 3 can be positive 3. And then we are going to expand the 4 cube. So the 4 to the power of negative 3 will become like 1 over 4 times 4 times 4, where it is equal to 64, 1 over 64. And again, that makes sense because 4 cube is just the inverse of 4 negative 3. Because with a negative exponent, it's just the inverse. So the same as 64 and 1 over 64, because that's the inverse when you do multiplication operation. And we will discuss a theorem that relates to the rules of exponent of a group. So let G be a group and let A and B be elements of set G. Then a to the m times a to the power of n is equal to a to the power of m plus n for all n element of Z. So by the way, if I say times, so I'm talking about the binary operation. So a to the power of m star a to the power of n. So for convenience, we are going to use times as a term for that in general. So a to the power of m to the power of n is equal to a to the power of mn for all mn element of integers. And ab to the power of n is equal to the inverse of b times the inverse of a, all to the power of negative n for all n element of the integers. So these are the um, rules of exponents for the group, and this is applicable for any group because there are a lot of groups, not just the basic group in real numbers set of integers. There are other groups like uh, cyclic group. So there are some other complicated groups that we cannot. It's hard for us to just simply imagine, but we can prove it and using these theorems. So we are going to prove the first statement that a to the power of m times a to the power of n is equal to a to the power of m plus n for all m and n element of integers. So here's the proof. So first we show that for all n, it is true for all m greater than or equal to 0. So if m is equal to 0, then automatically it is true because the a to the power of m becomes an identity, a to the power of 0. And so also the other side, a to the power of 0 plus n. And so that means it becomes a to the power of n is equal to a to the power of n. So that's understandable. It is true. Now for m greater than 0 for all n, then a to the power of m plus 1 times a to the power of n. So you might wonder, why is there plus 1? Because we are talking about greater than 0. So to make sure that it's greater than 0, we plus 1. We add 1. So it is equal to a to the power of m times a to the power of n. So is that so? Because of the plus 1. So if you plus 1, that means you add, you can rewrite it as a to the m times a, and then regroup. And then we can combine a and an, which is a to the power of n plus 1. And then we can combine them all back, so it becomes a to the power of m plus n plus 1. And then we can rewrite it, or we are going to do some commutative properties in the exponent. So we are interchanging 1 and n, so it becomes m plus 1 and then plus n. And so a to the power of m to the power of n is equal to a to the power of m plus n, because it's true with the m plus 1 for all m greater than or equal to 0 and for all n. So we're not yet done because this is still m greater than or equal to 0. What's lacking is m less than 0, so that it's complete. There is equals 0, there is greater than 0, there must be less than 0. Why is it separately shown? Because based on the definition, they have different definition. When it's less than 0, when it's uh, greater than or equal to 0, when it's equal to 0. So that's why it must be shown differently. So now suppose that m is less than 0. So this has a different definition as I have shown you in the previous slides. So when it's negative, when it's positive, and when it's 0 exponent. So then a to the power of m times a to the power of n will be like this based on the definition of negative exponent. And then we're going to combine them since they have the same base, a to the negative 1. So we can combine it as negative m minus n as the exponent. Then we are going to, since they are all negative, so we can rewrite it as a to the power of m plus n. And that is the proof of the first one. Now for letter B, where a to the power of m to the power of n is equal to a to the power of mn for all mn element of the set of integers. So we're going to prove this, so let's have the proof. So first we show that it is true for all n greater than or equal to 0. But again, of course, we are going to show as well the n less than 0 because it must be all for all n. So if n is equal to 0, then it is true. So you might wonder why, where is the m? Why is m not necessarily used? Because the n is in the outside. That's why, as you can see, there is a grouping symbol enclosing a to the power of m, and then n is there outside, so it is the one that should be shown to be for all n. So let us continue. If n is equal to 0, then it is true automatically because the a to the power of m becomes an identity uh, element, as well as a to the power of mn, it becomes a to the power of 0, so both sides will become an identity element. So that's automatically true. Now if it's n greater than 0, then it will be like this. We are going to add 1 for n, again because it's greater than 0. So we are making sure that it's more than 0. So we add 1. Then it will be like this. We are going to like expand the a to the power of m, since it's n and plus 1. So it's the same as a to the m n and a to the power of m. Then we combine m and n. Then we combine again, since they have the same base a, so we can combine exponents mn plus m. And then we factor out the m, so it will be m times n plus 1. And so a to the power of m to the power of n is equal to a to the power of mn. So as you can see, we have shown that it is true when we add 1, because we are trying to show that it's true if n is greater than 0. So for all m element of z or integers, and for all n greater than 0. Now we're going to show if n is less than 0. Then a to the power of m to the power of n is equal to, so we will apply the definition when it's negative integer, negative exponent. So if we simplify, m and negative n exponents can be combined into negative mn. And then we're going to combine negative mn and negative 1, so it becomes positive mn. And that is the proof for the for letter B. Now for letter C, this will be just short proof. AB to the power of n is equal to b to the negative 1, or the inverse of b times the inverse of a, times the negative n for all mn element of the set of integers. So here's the proof. So take note that a b to the negative 1 is equivalent to b to the negative 1 times a to the negative 1. Alright, so for n element of the integers, we have ab to the power of n. So we can rewrite it this way. We're going to separate the n into negative 1 and negative n. So it's the same result if you combine them. Then we use what we have taken note above. So we'll use that. B to the negative 1, a to the negative 1 to the power of negative n. So we'll just expanded the ab to the power of negative 1. And then we are going to, yeah, that's it. That's actually the last part. B to the negative 1, a to the negative 1 to the power of negative n. So we have proven it, and that is the proof of the theorem for A, B, and C. Thanks for watching and I hope you have learned from this video. Please support my channel by pressing the subscribe button and write the math topics you want to learn in the comment section.